So thank you very much for joining today's webinar. My name is Jules Reed. I'll be taking you through the webinar. Some of the key takeaways from today, you'll have seen in the flyers that went out, or the intimations that went out about this. What we'll be looking at is coring and core handling, mainly at the well site. And we'll be looking at the processes there and how those processes can affect core analysis. So that'll be one of the takeaways. Another one is how to, a little bit around some of the designs that you'll need to do to ensure that you meet objectives. And then some of the mitigating potential damage mechanisms. Of course, we've only got a limited time. We're not going to touch on everything. There are other potential mechanisms outside of this. As we go through today's webinar, I would encourage you just to use that question and answer page or button to ask questions. If there are questions that I can answer as we're going on through the slides, I will do that. One question came in, will we be sharing a slide pack? Yes, we can provide a slide pack that I'm presenting today. Okay, so let's begin. I have this switched to my clicker. So I'm going to be presenting. My name is Jules Reed. I'm currently the Global Technical Manager for Premier Oilfield Group. And some of you may not be so aware of Premier Oilfield Group. The group has been around for 5 or 6 years now. They purchased a number of laboratories, a number of companies, and one of them being Corex. Corex is globally known probably more within formation damage. It has been doing core analysis for almost 40 years, from starting out in Aberdeen in the UK, in Scotland. I myself have almost 30 years of experience. It will be this year, later this year in June. I began in Core Lab many years ago, and then probably the most productive time for me in terms of where I learned most was with ResLab as chief engineer of the laboratory in ResLab, looking at dynamic processes, relative permeability, wettability, capillary pressure, and EOR. But I've gone and I've been involved in almost all aspects of core analysis, and largely from a perspective of experimental design. About 5 years ago now, we published a book, myself and 2 colleagues at the time, Colin McPhee and Itzaskun Zubizarreta, looking at core analysis, and largely because we didn't see too much on the market in terms of SCAL and best practice SCAL, and so we decided that it was time to write those. So that's a little bit about myself. So what we'll do is we'll begin and begin to look through today's topic. Coring is not boring. That's drilling. Sort of. Drilling is boring. And I once was giving this or similar talk to a group of drillers in a company that I was working with, my previous company, Lloyd Register. And I thought, I can't really call this drilling is boring to a group of drillers. Coring's not boring. So I used to call it well begun is half done. And I had the thought that this had come from Mary Poppins, that this is a saying that she used to have. But when I looked into this a bit deeper, I actually found out there was Aristotle first said this. And basically, the term is meant to be, if we start something well, if we plan something, and we plan out what we're going to expect, and we put those plans into place, doing that before we begin is half the job done. So beginning properly. And quite often, in my experience in coring is that companies are not planning properly. They're not fully planning the core. And so what we'll do as we go through today's webinar is we'll look at, why are we coring? Why do you need core? And what's the purpose of it? And then we'll look at different coring considerations, the equipment and the coring types, some of the properties of parameters around coring. And in particular, what we'll look at is what can go wrong. Now, what you'll have seen in some of the text, I like the film The Matrix, and there was that particular quote from the Merovingian, cause and effect. Everything that we do has an effect on something else. And so when we come to core analysis does not begin once the core comes in the lab. Core analysis begins a lot longer before then. It begins in the planning stage of coring. Not even during the coring itself, but when we get to the coring, then things that happen during coring and things that we do during coring and during core handling at well sites and into the laboratory and have an impact on the analysis that we're going to perform. So there was an article in the JPT a number of years ago looking at core and looking at the value of core. And basically saying, look, logs cannot characterize a reservoir on their own. Coring is actually a small fraction of the cost of a well, and yet it becomes difficult to get management to see the value of taking core. But there's a lot more data in core analysis and in the core itself than many people understand. It confirms lithology and mineralogy. It calibrates our estimations from the logs, because the logs are only really estimations of properties. Yes, they're quite reasonable estimations, but they need something to tie it into the reservoir. It shows the fluid occupancy, and we can obtain mechanical properties. And that, for drillers, is actually key. Understanding the mechanical properties can help you improve how you're drilling in future, so that you get better drilling processes and better completion. But the main value, or one of the main value of core, is its understanding its properties to help in aspects of reservoir size, capacity, and of flow property. So this is just an image showing you, say, a reservoir, 1 mile by 1 mile, that's about 1,500 meters squared. A 200-foot section, so that's about 70 meters for those who work in meters. And if we assume there's 20% porosity, then that's approximately 150 million barrels of oil, which if you, a number of, couple of months ago, would have been approximately $7.5 billion. Now, small uncertainties in core, 1% porosity. Porosity is one of the biggest uncertainties. It's also one of the biggest weights on the value of that concession. So 1% porosity change in this scenario is about $375 million. So spending $500,000 to look at and improve our understanding of things like porosity, I would say is worth it. But why core? What's the objective of coring? And that is the fundamental question that should be asked before you take core. And it seems incredible, but I have known coring jobs to have happened where the people have just taken core because, well, we want to take some core. And You have to get to the fundamentals of why are you coring? What is its purpose? And different people will have different purposes. There are different stakeholders in there. There are different objectives. Geological, they may be about reservoir properties, porosity, permeability, hydrocarbons content. It could be about the geomechanics. It could be for log offsets, or it could be for looking at things like recovery factor, or for formation damage or EOR. So each of these different objectives may have a slightly different way that you would obtain core, or different properties of the fluids or of the assembly that you're putting together. And so the first thing that you should be doing is getting together into a meeting before coring and to look at those objectives. Look, there has to be, during the coring process, there has to be a synergy between the different people involved, between the drillers, the mud engineers, the people who want the data from the core, and the core technicians or coring technicians themselves. So we need to get all of these people here on the right, should be getting together into a meeting and discussing what is the main objectives. Each of these people have different objectives. And those different objectives will steer how they are involved with the core. So the drillers, they don't want core. They just want to drill holes. They're not, the coring actually comes and gets in the way of drilling. And drillers are, not all drillers, but most drillers are incentivized by how quickly they can drill the holes. And when core comes along, it gets in the way of their pay package. So they don't want core. The asset manager, he's trying to balance all of the costs. And so coring, again, is an additional cost to a drilling operation. And so but he may see the value in that. The people who want to understand the data, of course, they're going to be very interested in getting the core itself. And many people forget, or many companies forget, the reservoir engineer. Quite often, things like relative permeability are thought of years down the line after the core has been taken, rather than at the point of coring being taken. We might need to know some of these properties. And so what we'll do is we'll start looking through different parts of coring and of those properties. We'll need to consider how the different materials in coring may affect. So you have different coring heads, you have different core barrels, you have different lengths of core, different types of core catcher. So if you're in an unconsolidated system, you will need a different core catcher than if you have a consolidated core. If you're in a fractured reservoir, you'll probably need different type of core barrel liner, and also maybe a different type of catcher than if you're in a consolidated sandstone. And the mud system, we'll look at how some of these things impact the core and its properties. And there are different types of core that we can obtain. So there's conventional coring, Y-line coring, or sidewall, and each of them have their drawbacks and advantages. And so before we start considering when we're coring, we need to consider, well, what type of core do we want? And that will guide some of the decisions of what properties we want and what materials we want in place. So, and one of the first things that will happen, one of the major things from the coring process is fluid invasion. We want to minimize that. We don't want massive invasion. And the picture on the left here is just showing you a UV light image of a core, showing where the mud has invaded into the core and how far into that core the mud has invaded. We want to minimize that. It wants to be a thin layer around the outside or no invasion at all, because we're going to have to take samples, and the invasion may impact, as we'll look at later, invasion may impact on the properties. And sometimes filtration may occur, Sometimes it will always occur, and we'll look at times when that will happen as well. But one of the ways that we can minimize invasion, so one of the mitigating processes for that, is by low invasion coring tools. And the picture on the left shows you a little of those tools we have in here. This is a low invasion head. So in a low invasion head, the fluid, the mud fluid, comes out onto the surface outside of the core to be more transported away. In a standard core head, much of the mud is piped in here, almost directly onto the surface of the core, and that's where you might get this massive invasion that you're seeing on the left. So I would always recommend, almost without fail, a low invasion core head. But the core liner or the core barrel is also important. And the various different barrels, various different equipment that you could use for this. We've got fiberglass, we've got aluminium slick or aluminium fluted, there's a half moon, and there's jam buster, and all of these have different properties, have different purposes. And so ones like the fluted liner here, they have little gaps down the side that allows for fluids to escape around the outside of the core. So these are particularly useful in things like gas reservoirs, where you want to improve the gas escaping from the system. Fiberglass, well, I find the fiberglass is often good for unconsolidated systems, but you're going to be limited in terms of the length of cores that you're taking. You're going to be running in shorter cores. Half moon is one that's been around for maybe 10 years. This allows you to, at well site, open up the barrel, look at what's inside, and close it again. So very useful if there's a process that requires you to observe the quality of what you're getting before going on. Someone's asked the question if low invasion heads are special and easily available. Most coring companies these days have a series of different low invasion coring heads, and I would encourage you to discuss with the coring companies. And then jam buster, and I'll come on to this one. I'll show a video of a short video of that a little later. Also, other things in terms of the half moon is that you get this one called half moon on ice, and it's particularly good for maybe some slightly more unconsolidated systems, because you get less friction here. So it allows the core to move inside more freely. This is a list of advantages and disadvantages of some of the different types of core barrel material and the different types of barrels that are available there. There are other types of barrels, it's worth sometimes doing a bit of research or discussion with the coring companies to find out what they have available and what its purposes are. And we'll give the slide pack so you get to see this one. I'm not going to go through it in particular depth today. But there are some different types of core, and this comes back to the objectives. What are the objectives of my coring process? And sometimes it may not actually be for the core itself in particular. It might be about the core plus the fluids. And so things like pressure coring and sponge coring, they're particularly relevant for if we're wanting to look at things like residual oil saturation. So that's the primary application for those. Looking at the oil in the core and how these work. Basically, the pressure barrel captures the core. It maintains pressure from core depth up to the surface. You can control the pressure, so you can gradually release the pressure with this control valve. But while you're doing that, what you want to do is have some gas meter, because as you bring the core to surface, the properties of the fluid, whether it's gas or oil, will change. If you have reservoir oil, once you reach the bubble point, you'll begin to produce gas that will come out of solution, begin to be produced out of the core and up, and you can monitor the volume that's being displaced as you bring to surface and as you control the pressure. So what we get from this is we get this total gas volume. We can then measure the core itself and measure the volume of oil in the core, plus the volume of oil that any oil that has come out into the surrounding barrel, and determine from the core then the pore volume, and put it all back together into saturation. So the saturation is the volume of the oil plus the volume of gas, all together combined back up to reservoir properties, and that gives me the saturation of oil. But of course, this then comes on to selection of fluids, because if I want to monitor oil, then I don't want to look at having oil contamination from my mud system. So then I want to use a water-based mud. There's a question about the barrel from Baker Hughes, whether that's still in use. I'll maybe come back onto that later, in which particular barrel, or which barrel in particular. Sponge coring, that's similar to the pressure barrel, but what you have is, instead of a pressurized system, you have sponge around the outside of the core, so that any oil pushed out of the core is captured into the sponge. Again, you measure the saturation of the sponge, and as well as the saturation in the core, so that you get this. And there was a paper back in 2004 that looked at this process, and the graph on the right is showing the correlation between NMR residual saturation and the residual saturation of the core, and showing you this excellent correlation. Then we have sidewall cores. So that was conventional cores, sponge and pressure barrel cores. Then we have sidewall cores, and with sidewalls there are two different types really: percussion and rotary. And within rotary there are two other types as well. So the percussion, the way that works is basically firing a tube out into the formation. It captures a piece of rock, pulls it back into the tool, and pulls to surface. With the rotary, you have a rotary tool like this that comes out from the tool. Is basically like a mini core or a plugging machine. It cuts a core and returns that into the tool and brings to surface. Now we would generally tend to recommend the rotary cores over the percussion, because the percussion, you can imagine, it's basically shooting like a bullet into the formation wall. It generally begins to fracture that, it weakens the core, and it does not have the same mechanical properties. One of the other things as well about sidewall cores is it's taking cores from the area that has been most invaded and most impacted by the mud weights and fluid rate during coring process. You can get these big sidewall cores. So a rotary sidewall core here is usually 1 inch by 1 inch, 1 inch diameter by 1 inch length, maybe a couple of inches long. But these Max Core or MCST cores or XL Rock, depending on which company is taking them, these are 1.5 inch in diameter and generally roughly 2 inches long, and they're bigger. But they still have the same problem as the smaller rotary cores, is that they're coming from that area of the wellbore that has been highly impacted, and depending on what you need these samples for, they may or may not be able to give you the properties. So one of the things that no rotary sidewall core can give you is directional plugging. And sometimes that's important, because if we're taking samples from a rock, then we can have, this would be called parallel to bedding, or a horizontal core. This would be a vertical core. You can't really get vertical cores from rotary unless you're in a horizontal well, and it's perfectly horizontal and parallel to the bedding of the reservoir. And this would be samples that don't fill either of these. So this is horizontal permeability, this is vertical perm, and these are somewhere in between. And if we get a permeability that is somewhere in between, that may not be describing and may not be able to correlate against other permeabilities. So then we have, these are showing you the possible damage mechanisms or different types of damage that can occur. Just a few questions coming in, which I may come back to later, and we can discuss those later. These CT scans are very useful in core analysis to look at the quality of the rock that has come into the lab. And from the CT scan, you can tell if they appear damaged. You can tell what type of damage that has occurred. So this on here on the left is from gas expansion. Two forms of gas expansion patterns. One of them is this dendritic, like root type of breakage and fracturing of the sample, usually from the center of the sample, or this one here, which is I call the onion peel. And basically, this one here comes from invasion of the mud into the outside of the core, and that invasion stops the gas from expanding. The gas then peels off that outer layer because of the pressure that is building between the gas and the outer side of the core as you bring it up to surface. This one here is from improper handling at the well site, and I'll show you that in a bit. This concentric, if you start seeing fracturing beginning to circle in from the outside towards the center, that's basically a jam. And so the core barrel, which should be sitting stable in the center, has begun to twist along with the drill pipe and starts to twist the core, and so you get this twisting of fracturing. And then this one here, this chevron, not Chevron the company, but this pattern, this V-shaped pattern called a chevron, probably comes from transit or handling damage. Somebody dropped the core. And of course, we don't want that to happen. And all of these things will impact the quality and the properties of the core. So let me show you this Jambuster video. So this is just showing you what the Jambuster system does. It's a telescopic liner. It has 3 different layers. So as a fracture occurs, it shears off some bolts or nuts inside, like this, and then allows the core to be transported. And what this does is it allows up to 3 jams before you have to bring to surface, because the time tripping in and tripping out is the longest period during coring. It takes up a lot of time to trip in and out. And so if we can save time on tripping in and out, we can save a lot of money. One question has come about the size of rotary sidewall cores, and can they be used for scal? Again, they can be if it's the only material that you have. I generally don't recommend sidewall cores for advanced properties. You always have to have in the back of your mind, things may be damaged, and we'll come on to that type of damage later. And when we get onto chemical damage, these days with the type of fluids that are being placed down into the holes, it's more and more critical that we look at the impact that those chemicals have on the core. So one of the things that we want to do to try and help is when we're coring, we need to be looking at and monitoring the different parameters of the coring process, of our rate of penetration, the weight on the bit, the torque, so the stress that is being having to place to put into the bit turning, and the mud rates, etc. All of the properties that you would be looking, because we want to know whether we have to stop coring or slow down coring to make sure that we're getting good core. You may have to adjust the core length so that if you find that you've got a very good process, then you can go for quite long lengths of core. Otherwise, you have to trip in and out and get shorter lengths. Adjust the barrel types, maybe. Definitely adjust the mud weights. All of these things have to be considered before we start coring or during the coring process. And if you haven't thought about these before you start coring, then it may be too late, particularly if you're in an offshore situation. You cannot change the barrel types just like that. That has to be pre-planned. And you may need to adjust the well site handling for what you find. So the whole process has to be fit for the purpose that it's designed to do. These are just some more pictures showing you the extent of potential physical damage. These are from probably jamming, and you can see here this rotating fracturing, starting from an outside and rotating inwards. This comes from jamming. Then you want to try and mitigate. So things you can do to stop gas expansion, you want to slow down. Now, many of the coring companies, they will have rules of thumb of the type of tripping rates that you want to use. What we would recommend, or what I would recommend, is actually model that process. There was a paper in 2011 by one of my co-authors, Zubi Zaretta, co-authors of the book. And they looked at using computational fluid dynamics to model the core. And what we do there is we build a mesh of the core, a simulation of the core. We apply the core properties. We also apply liquid properties. We may also simulate the mud cake. That becomes important, as you'll see in the next couple of slides. And once we've put all the properties on there, and one of the big properties to consider is the tensile strength of the core. And the tensile strength is basically equivalent to the unconfined compressive strength. It's about 1/10 of the unconfined compressive strength. So if you have some estimations or pre-knowledge of what that core properties are going to be, you can model them. And on this graph here, we've got, on the graph here, we have the critical strength. That is the tensile strength of that core. And then we're modeling here the reduction in pressure as we bring the core to surface. And in here, the blue is the differential pressure. That's the pressure of the gas. And as you can see, the pressure of the gas is very low compared to the tensile strength. So that's going to be no problem. But that's modeling it without the mud cake. What happens when we model it with the mud cake? Well, that same process modeled with the mud cake in place, we begin to cross the critical stress line here after about 5.5 hours or 5.25 hours. That suggests that we may begin to fracture the core. And so what we do is then begin to look at optimizing that core run. And what we can actually do is, this data here at the start. This is the plan from the coring company of how they will bring that to surface. So they slow down here and they slow down here. They didn't need to slow down yet. They could have continued this line because there was no problem. And so what you can do is actually shorten some of the times deep in the reservoir, because as you bring it to surface, as you get closer and closer to the surface, you have more and more problem from actual gas expansion. There's a question about the extension of the fractures from foam. I'll come on to that later. So what we're doing with this then is finding the optimal times where we keep the pressure, differential pressure below the tensile strength of the core. If you model this for shale, and this was done in the paper, what you find is you can never keep the differential pressure below the that critical strength line. So in shale, you're always going to fracture the core. So what you generally need is you need longer tripping times for lower permeability. As you get closer to the surface, you need to slow down, and the differential pressure, the gas begins to expand exponentially. And you can do this, and I have done this not just for gas but for oils. If you know your equation of state, or you have some way of estimating the equation of state of the oils and how much gas is in the oil. Okay, so other types of fracturing that I showed earlier, this one here, that comes from this type of handling at surface. Hopefully none of you are doing this anymore. You're properly conserving and putting the core onto a cradle to keep it from bending, and then laying it down properly. Then once you're laying it down, what we would tend to recommend is to cut the core into 1 meter sections. That makes it much more easy to handle. Plus, you're not going to get the bending like in the picture on the left here. The core won't bend in a 1 meter section, but it will in a 10 meter section. The barrel will as well. And this is what it will look like. You want to preserve that. You want to seal it off from the atmosphere, and so you're preserving and cutting it off from exposure for its trip back to the laboratory. There are different types of stabilization. I don't really have time to go into the different types here, but generally the two preferred are gypsum or foam stabilization. And that comes onto that question about the foam. So this is foam stabilization, and gypsum's there on the left bottom pictures being poured in, and it surrounds the annular space between the core and the barrel, and then solidifies. And on the right, you have foam injection. And what you see in the foam injection, you've got foam poking out at different parts along the length of that barrel. That's because they've drilled holes into the top of the barrel to allow the foam to expand. Because as you inject foam into the barrel, the foam will expand as it solidifies. And if you have an unconsolidated system or a fractured system, and you inject foam without these points to allow the foam to expand outside, then it will begin to push the core apart. And so that's what happened in that earlier picture that the question was referring to. The core was fractured, then injected with foam, and the foam pushed the fractured core apart even more. So exacerbated the fractures. I would then suggest you place the core into stabilization containers to transport it to the laboratory. These should be lined to stop shock, stop damage. Remember the chevron type damage, to stop this core from knocking onto anything. And we suggest putting a shock tag or a shock monitor into there so that you can see how much shock that core has had as a function of the time from well site to the lab. So I mentioned earlier the need to consider. There's a question: what is tripping rate? So the trip rate is the rate that you have to pull the core from the bottom of the coring point up to the surface. That's the trip rate. It's also called pulling out of hole rate. And that needs to be done carefully. So we've looked at physical damage. Let's consider chemical damage. Mud additives are in all muds these days. They can be emulsifiers, asphaltic bridging agents, different types of chemicals. There could be anti-scaling chemicals. Various different components go into those muds. And we need to be careful of some of those, and I'll show you some of the impacts of those. We also want to stop oxidation. So that's the core, or the oil, when it's exposed to the atmosphere, it can begin to change, and that can impact the core properties and or the fluid properties. And we want to minimize that. That's why we were suggesting the preservation. So we saw in the early ones, placing caps on top. That stops it from coming into contact with the atmosphere. And so we don't want drying or too drastic changes in temperature. So how do we stop that? Well, one of them is to minimize mud additives during coring. That requires checking the mud composition, and it also requires the well site geologist, and this is why I'm saying you have to have buy-in of all the stakeholders and the well site geologists to be aware of needing to minimize the additives and to discuss that with the mud engineers. And if what we would also then suggest is invasion analysis, so that you consider the core and look at how much has been invaded into the core. How do you do that with some of the mud systems? If they're too similar to your reservoir fluid properties, your formation fluids, you may need tracers. And I'm not going to discuss tracers today. I'll discuss a little bit about it at the end of the necessity of it. But why is it important? Well, chemical damage will generally change wettability. And the wettability changes the sample properties. And it will change properties like relative permeability, which is an important input into the reserves calculation and to modeling our production over time. So, and correct wetting is essential. So if our core objective has anything that requires proper wettability, then we need to be careful what fluids that we're placing into our coring process. There's a question saying, should this be acquired from the coring services in the planning phase? Yes. So when we're looking at things like tracers, and the muds come from the mud company, but tracers can be added by the coring or the core analysis companies, and the tracer testing can be done by the core analysis companies as well. Another thing that correct that wettability changes is capillary pressure, and that's how we actually determine a stock tank oil in place. So it's a fundamental impact on our calculations of the hydrocarbon or the size of our reservoir, hydrocarbon content. And it will change the residual oil saturation as well. So it has this big impact. And some of the additives into mud are ones like this, EasyMul. It says there it's an oil wetting agent. Now, it's potentially not just the surfactant on its own, it's a surfactant together with all the other additives in that system, but it changes wettability. And I won't go too detailed onto this plot on the right, but the dotted line there is what should be strongly water wet. And after cleaning in core analysis, we should be trying to get to this stage. But these samples here, in contact with some of these mud additive agents, are not water wet anymore. They're very oil wet. So this, seeing this kind of sample would be oil wet. This is water wet, and this is what we were expecting to see. So we need to preserve samples to stop some of those oxidation which can change those properties. We need to try and minimize the amount of additives going into the coring mud. And this comes into then different handling techniques. So generally, I would recommend waiting to handle the core once it gets into the laboratory, because you've got better conditions in the lab to do that. But there are sometimes you have to do it at well site, and some of them, and those in particular for Dean Stark. So understanding the saturation, Dean Stark is for obtaining water saturation, or if you want to understand your water salinity from resistivity of water testing. Part of the reason for this is because this core will get invaded, and if we leave it time to get from the well site to the lab, then some of that invasion may migrate from the outside to the inside of the core. So what we would suggest then is take core plugs as immediately it comes to surface. When you cut the core open into the 1 meter barrels, take a plug in the center, and then it's in the area that is least invaded. If you remember back to that picture of the invaded core, then the center part of that core is where there's least invasion. And what you're doing is then, as soon as the core comes to surface, you're taking a sample from a region that is least invaded. And that's what we want to attempt to see. So what is the impact of that? What are the impact on how do we monitor that saturation and some of the saturation changes that are happening? Because during the coring process, we will have invasion. So this is just showing you the sort of changes that are happening. Some of these changes we cannot control because it's a function of things like gas expansion. And as gas expands, it's going to push liquids away. And so there will be changes in saturation as you bring it to surface, and we can't stop that. Unless we do, say, pressure coring, and we bring the core to surface in a pressure barrel with all the liquids inside still. But at some time, we're going to have to do some opening up that barrel. So this is showing you in a water-based mud, in an oil reservoir, what will happen. So maybe originally, we start off with some water content and some oil content. During coring, some of that water may invade into the oil. It will push some of the mobile hydrocarbons out. And so some of the water is now, it's not just water, irreducible water, it's water plus mud water. Then as you bring to surface, the gas begins to come out of the oil. It expands and it pushes out some oil. It might push out some of that water that has just come in as well. And so you get to the surface and you have a different saturation at the surface. How do we determine the difference? Well, the only way we can determine the difference between these two waters really is by tracers. We put a chemical into the mud water so that when we find that chemical inside the core plug, we know that it's been invaded. And if we know the concentration of the chemical in our mud, then we can see the concentration of chemical in the water here. We know how much it's been invaded. And the same in a gas well. In a gas well, you'll have significant invasion with a water-based mud, because that gas well will be water wet and it will pull water in. And as it comes to surface, gas will expands, pushes some of that water out. And the same with these oil-based or synthetic-based muds. I'd say today, there is no such thing as an oil-based mud. If you go back 20 years, many oil-based muds, proper oil-based muds, would be diesel-based. And from a health and safety perspective, today, it's rare, if ever, to find a diesel-based mud system. So what they tend to be these days is a synthetic-based mud, which is just a paraffin oil together with then emulsifying agents to try and hold the paraffin oil and some water together. some of these synthetic-based muds can be up to 40–45% water content. So it's important to understand the composition of the mud, because if that invades in and you've got emulsifying agents in this synthetic-based mud, it can change the wetting properties of the core. And so it's important to understand what the impact of those are going to have on coring before you start coring. So, to conclude, core analysis starts before coring. It's important to understand the objectives. It's important to plan. It's important to have everybody who's going to be involved in that on board and understanding why we're doing what we're doing. There are various things that you can do to mitigate against potential damage, and the type of damage that you will observe can be physical, it can be chemical, or it can be to the objectives. Your objective is to get water saturation, and you use a water-based mud and get invasion with no traces. The whole of your objective is lost, because there will be no way that you can determine what's from mud and what's from formation. So, and remember, this is just the start. Well begun is half done. Core analysis requires a continual thought process throughout the whole program. It's not good just to start well and then forget about it and let it go on. You need to start well and you need to continue. So thank you for your attention today. Now at this point, I would have had somebody coming on and going through the questions with you. So what I will do is I will look through the questions that have come in just now. And I'll try to answer as many as we have time for. I would say we've maybe got, although it should have finished around about now, with the late start, we've maybe got 10 or 15 minutes. And any questions that I don't think that we have time to answer just now, what we will do is we will take all the questions and we'll put a list of answers and send it out with the slide pack. So one question was, Jules, for unconventional core analysis, such as shale permeability using crush sample protocol, do you think we need preserved cores? Formation is surely mostly shale. Well, that's a good question. For unconventional cores, then there is a lot of analysis done on crushed. And if that's the only thing that you're doing, then potentially it doesn't matter so much the factoring. The pressure barrel actually came back probably about 2006. It had been maybe 50, well, from my experience, about 10 or 15 years before, until the previous one before 2006. And 2006, it came back for the shale process, but not for looking at the core. It was brought back particularly for looking at the gas content and obtaining the gas content. However, there are big questions around whether the shale, the crushed rock, is representative. It has quite a high potential variance in permeability. So sometimes you may want to try and obtain a more consolidated core to look at a comparison between crushed rock properties and actual properties on the whole matrix system. The next question, have you used core vault technology from Halliburton in carbonates? I didn't show it. I do know of it. So the core vault is basically similar to pressure barrel process, but it's from Halliburton. It's their technology. I haven't been involved with one yet. There are some other ones that I didn't mention here as well. So CorePro, they had one called Liquid Trapper, which I think they don't do anymore because it it had rubber seals that came and sealed around the sample, and sometimes because of milling, that sometimes that worked and sometimes it didn't work. So, but I think CorePro have an alternative to that as well. Yeah, it's worth speaking to the coring companies to find out what equipment, if you have a specific need, find out what equipment they have that might help against those objectives. Next one, core liners are used with wireline coring and not in conventional cores. Is that right? No, actually, core liners are used in conventional cores. Years and years ago, there were no liners in either. But nowadays, there are core liners in almost any core, wireline, or conventional. The next one, Ikram says, if sponge core is taken with oil-based mud, how are we going to be sure that the oil captured in the sponge is from the core or from coring fluid used? Well, that comes down to that thinking through the process and before you core, deciding what fluid you're going to be using, because you cannot use an oil-based mud really with a sponge core. What you're looking for is water, you don't want to add water to the system. If what you're looking for is oil, you don't want to add oil to the system. So those just fundamental things like that guide the usage of things like fluids in the system. Next question, have you found that the larger, I've already answered that one, the larger rotary sidewalls can be used for scow. So the next one, core pulling is critical. G, stay with coring engineer at the floor. Yeah, I would say generally the well site geologist. I have I'll maybe put a longer answer to this, but I've experienced where the well site geologist has actually been detrimental to the core. The core hands had a plan of bringing it to surface. The well site geologist overrode the plan because they didn't think there was going to be a problem, and the core came to the surface. Actually, the picture that you saw with it massively fractured, and where we say it was then further fractured by the foam, came from that particular job where the well site geologist ignored the plan and just brought the core to surface very quickly. And I'll maybe put some more details into that of why that was done and why the well site geologist thought that it would be okay to just ignore the plan. There's a question about the DP chart. So I'm not sure which of the charts. There were a few. There are these ones here, or this one here. So this and this are basically the same charts, but they've just been shown in different manners. So the straight line that I'm showing here is the critical strength. What I'm showing, what I'm showing in here is then the critical strength is the purple line here. The red line is actually the internal pressure as you bring it to surface, or the fluid pressure as you bring to surface, and the blue is the differential pressure added on to this pressure, the actual fluid pressure. In my book, or in our book, the Core Analysis, the Best Practice Guide, you said it's risky to use sodium hydroxide in mud because it can change wettability. That's correct. Yeah, sodium hydroxide is an alkali solution, and one of the methods of EOR, so of changing wettability, is to do an alkali injection. So yes. Do I have any alternative to sodium hydroxide? It depends what you're wanting to do. So that's maybe something we can, if you have another comment, we can discuss outside of this that process. It's important The next one, it's important that the driller understands why the core is not pulled too quickly. He has a hand on the brake. That's a very good comment. Thank you, Richard. Yes, it is important that the driller, I said right at the start, it's important that everybody is on board with the procedures and why we're doing those procedures. Because this core is worth what? How much is it costing to take the core? Depending on whether you're onshore or offshore and how deep you are, that core could be costing anywhere between $200,000 to $500,000 to $1 million to acquire. It's expensive. And if you pull that too quickly, or if you are doing things that are damaging the core, you're throwing away, and this is part of what I was saying in some of the material beforehand, why companies might be throwing away millions of dollars. Not individual companies, but as a whole across the industry, we could be throwing away millions by just ignoring core plans and core procedures. The next question here, you have dealt with core cutting, retrieving and handling in great details, but are your personnel in the field equally trained, knowledgeable, and caring in core? It depends where you're going to. Of course, I have not been involved at the well site for a long time. I have 30 years of experience, but there are some companies whose core hands at the well site have as long. And of course, it's our experience and our experienced personnel, it's our requirement to train those people in understanding what we have learned over the years. It's always good to actually ask who's going to be doing that. If it's important to you that you have a good quality, then you should specify certain people. But of course, that's going to be more expensive because that experience comes at a cost. So you may be having to pay more for the more experience. Next question. Have you used core vault technology? Oh, sorry, I've already done one. There's some, what are the pros and cons? What I will do is I'll send out the pros and cons of the core vault technology. Next one, how often do we use oriented plugs for analysis and objectives for doing so? Well, it depends again. So that depends on the findings of your reservoir as you're doing your reservoir characterization. How important is it to know the vertical and horizontal permeability? And that will guide whether you use oriented plugs or not. But if you're looking at say horizontal permeability, well, generally your vertical perm is roughly 1/10 of the horizontal perm. If you were to just calculate this, and so having 1/10 of the permeability compared to the actual perm could be significant. So you don't want something that's in between. So it could be very important. What would be some of the most significant challenges during shale coring? Some of the challenges are the material itself and the heterogeneity of the material that you're coring through, changes in composition and in properties, in terms of its effect on things like ROP and torque. Well, torque in particular, it can have a massive impact, and you may suddenly go from maybe a fairly softer formation into a more harder formation, and it can be quite difficult knowing whether the changes that you're seeing and monitoring are coming from problems or because you're going into different heterogeneous features. I've got 11 more questions here. What I will do is, because of time, What we'll do is for the remainder of the questions, I think I will put those out. We will answer those questions, send it out to your email addresses along with the slide pack. And I just want to take the opportunity to say thank you very much for attending the webinar today. Hopefully you've found it interesting and useful. If you have any other questions, please feel free to contact me. My details are here at the end here, so my email address is here. It will be on the slide pack that comes out there as well. So if anyone has any other questions, please feel free to contact. And what we're doing at the moment is these webinars. We're looking at running a webinar every week. At the moment, myself is every other week, so every fortnight I'm doing one. So in a fortnight's time, I'm going to be looking at leveraging legacy data and maximizing metadata in Core. Next week is going to be our one on formation damage. So from Justin Green, who's an expert in our formation damage group, will be speaking next week. So keep look out for the forthcoming webinars, and thank you very much for attending. So take care, everybody. Stay well.